Today I'm going to teach you how RAG works and how can you implement it in your projects or workflows. So currently the LLMs have a very large context window, but this doesn't mean that we have to use them all. For example, OpenAI has 1 million tokens on the context window, but they recommend to use roughly 250,000 of them to preserve quality on the responses. So let's see a practical example. Imagine you have your code documentation or any type of documentation you want to search. And we have thousands or hundreds of files, okay, markdowns, PDF, and more. So in the old mode without RAG, in order to search or ask any question about this documentation, you will have to attach all the documents in the context prompt. So that's not the best way. In fact, this is a bad idea because we don't have to fill the context with unrelevant information. For example, if we are asking for any API guide, it's not relevant to attach any MCP or I don't know, some other libraries information there. So RAG systems helps us to find and retrieve only the information we need. Here I have an image which explains it very well. Here we have all the documentation I just mentioned you. So here is a PDF, markdowns, wherever. We're going to use markdown for this video. And the idea is to store all these markdown files into a vector store is a database which contains embeddings and chunks, actually embeddings of our documents. What is an embedding? To keep that easy, it's a series of numbers and vectors which corresponds to your content, basically. We transform content into an embedding vector index. How we can do that? Is it difficult? No, it's very simple. There are plenty of models that we can use to convert that content into embeddings, and they are very fast and very cheap. So once we convert all our content to embeddings, we can store them into a vector store. And once we got this, we can use natural language to ask questions to our vector index, and we'll retrieve only the relevant chunks. For example, if we ask for any API, it will return the chunks relevant to that API. And then, and only then, we can use that context to complete our prompt and our response. So that can sound very difficult, but it's pretty easy. We only need a model to convert those embeddings and a vector store, which can use Postgres with a pgvector extension. So I use DB, which I can install Postgres very easily. If you use any other tool, it's okay. You only need Postgres and pgvector extension. So let's try this. We're going to use OpenRouter to make our LLM request as well as the embeddings and the responses. So I'm going to create an IP key and save it for now. Now I'm going to use Codex to start a Python script to show you how it works. I'm not going to show you all the code because I think it's irrelevant nowadays to show how line by line how the code works having AI. So first of all, we have to create the embeddings and the pgvector database. So I'm going to use docwriter.a entire platform documentation, which is, by the way, the sponsor of this video. DocWriter is an AI documentation platform which can generate the entire documentation for your code base in just seconds. It creates API blocks, diagrams, README files, and all you need to store and manage your code documentation. So I have all these README files here, which is the DocWriter documentation. And now I'm going to create a new Postgres database to start working in. All right, we have our documentation and our Postgres database with just a blank database. So let's start with the Python script and let's start with the embeddings. First of all, we have to parse all those embeddings, all those content, and then we can ask questions and create responses on this. So let me prompt that for you. You have the markdowns for the docwriter.ai documentation platform. Using OpenRouter API key, which I'm going to send you, create the embeddings using OpenAI small model and save it to our pgvector storage using RAG database. So let's go. What is the OpenAI small model? So there are different embeddings model that you can use, but OpenAI has text embedding 3 small, which is very good, honestly, and it's very fast and cheap. So we're gonna use that. Let's wait until Codex finishes this script and I will take a look at the code and let you know. All right, so it took 8 minutes to process that. Let's see how it works. As I mentioned, basically, this is parsing all our markdown documents, sending to OpenRouter text embedding 3 small model, and that model will return an array of numbers, vectors, and the only thing we have to do is store those vectors to our database. So let's try how this works. I'm gonna copy that and yeah, run it. All right, cool. That was fast. So you're seeing chunks here. That's because each one of the documents is stored with different chunks. It's not stored as one row on the database. You also can see dimensions, some numbers here. I'm not gonna explain all of that because vector storage can be really large and difficult to explain, but in basic terms, we can use just the default parameters for now. So let's see how the database is storing this. You'll see a ton of different tables here. These are the vector store, the pgvector extension, sorry. And we have our table here, rack chunk. What we'll see that here, the collection name, the source path, and here we have the embeddings. So that's it. That's our content in vector format. So we have it. As I mentioned before, the content, the markdown files are separate by different chunks. So this is useful on the retrieval phase because if we, for example, in the audit log, we can only retrieve the CSV export and we don't need the other ones, for example. So what now? Let's back into the image. So we are here, basically. We have our documents, our embeddings, and our vector store where we are storing all that embeddings and all that content. So what now? Now we have 2 different requests to do. One is a question to our vector store to retrieve what we want exactly, for example, API endpoints or methods, wherever. Once we have all that content, we'll have some chunks, only the only one relevance. And then once we have this information, we can prompt to the final LLM to create the response. So now I'm gonna back to Codex and see, all right, now we have the embeddings part and let's see how this embeddings and chunks works before creating the final LLM request. So create another Python file to show me how embeddings works with natural language, how we can search them and retrieve the chunks. All right, meanwhile, I'm gonna show you what was the cost of processing that. So we made today 14 requests. These are the 14 documents which we processed. So this is roughly, let me see, it doesn't even show the cents. So less than a cent of a dollar. And we process 45,000 tokens on those documents. So let's wait until this completes and I will show you how the embeddings search works. All right, so here we have it. Here we have some examples about how to use that. Basically, what we're doing here is when we ask for anything with natural language, For example, how do I connect a Git repository to a space? This has to be converted to vector language. What is the vector language? It's the embeddings. So this phrase will be converted as embedding, and those embeddings will search into our pgvector storage, into our embeddings, and search what are the best relevant content. So let's try it out. We have an interactive mode, so let's try that. Natural query language, let's copy, that. So our query is that query embedding using the same model. So that's the embedding for our query. This is vector language for our question. So what happened here? Retrieve 5 chunks. What happened here? So within this documentation, our vector store retrieve 5 chunks, and we have some information here. We have the similarity and the distance. I'm not going to explain the distance because it's a very technical property, but I'm going to explain the similarity. You can imagine what's the similarity, okay? It's basically a score, okay? The similarity goes from 0 to 1. As much close to 1, better the match between the query and the content, okay? So, for example, if we have here similarity less than 0.5, for example, we can just discard those chunks because maybe are not relevant. We can tune that a little bit for our purposes, okay? So what's left now? Why we did all this? Because now we have the specific chunks, the specific content to our question. So let's back into the image and let's back in how do I connect a Git repository. So I want to know how to connect a Git repository into a space. So instead of attaching the entire documentation to our prompt and just wait for a quality response, so now we have the vector storage, we can use only the relevant chunks returned from the vector storage and attach only those relevant chunks to our prompt request. So that will return a very accurate and with a high quality response. And because it only has the information, the relevant information from our vector storage, only have the relevant information from the specific markdown file, not all the documentation. So the only thing we have left is, build a prompt. But that's the easy part. Now we have the relevant chunks, we only have to attach here, and we'll have the response. So that's how our RAG system works. And that's why RAG is so important nowadays. Because imagine this is 1,000 files. We don't have enough context to attach all that files. The embeddings works with content, not just markdowns. It works on PDFs, markdowns, images, wherever you need. It's content. So that's a very basic overview about how RAG works. With only that, you can build very complex systems in all your platforms and projects. But as I mentioned before, there are a lot of different things you can do. There are a lot of parameters, a lot of tune options that you can use. There are vector stores where you can store those databases and scale. So welcome to the RAG world. I hope this tutorial will help you and solve a lot of your problems. Remember to check out docwriter.ai, which is the sponsor of this video. And see you in the next.